Hello everyone, welcome to Chem analysis. This is my second video on Huckel molecular orbital theory. Here I will mainly discuss about delocalization energy for a cyclic system like cyclobutadiene or benzene and determination of hybridized orbital from a given wave function. First, let us calculate the delocalization energy for these two cases. Now, since this is a cyclic system, as in my previous video I have discussed about the energy of different MO for cyclic and acyclic molecule, such as for cyclic molecule the energy expression for different MO, that is different molecular orbital, is like alpha plus 2 beta cos 2k pi by n. It is the energy for different molecular orbital for cyclic molecule, where alpha and beta are constant, k is constant whose value corresponds to 0 to plus minus 1 to plus minus 2 to and etc. and n is the number of carbon atoms. Now, if we calculate the energy of the different MO for cyclobutadiene, we can get that for first MO, since it contains 4 carbon atoms, there will be 4 molecular orbital. And for first molecular orbital, energy will correspond to alpha plus 2 beta. Here k will be equal to 0 and n will be 4, since number of carbon atoms is 4. So this value will be 1. The total value will be alpha plus 2 beta. For E2, the value will be, here k will be plus 1, that means cos 2 pi by 4, that means cos pi by 2, and the value of pi by 2 is equal to 0, so this is alpha. Similarly, E3 will be also, here will be minus pi by 2, that means cos minus theta is equal to cos theta, so it will also be alpha. And the energy of the E4 will be cos 2 beta cos, for k we have to put plus 2, that means 4 pi divided by 4, that means cos pi, and value of cos pi is equal to minus 1, so it is alpha minus 2 beta. So the energy of the 4 molecular orbital for cyclobutadiene is like this. If we draw different MO, we can see that this will be alpha plus 2 beta, and there will be 2 degenerate MO for which energy is alpha, and the last MO energy is alpha minus 2 beta. Now in cyclobutadiene, the electron, there is 4 electron and they will distributed like this. So total energy for cyclobutadiene is equal to 2 into alpha plus 2 beta plus 2 alpha, since it is for one electron alpha and another alpha 2 alpha. So in total there will be 4 alpha plus 4 beta. Now to calculate the delocalization energy, it is not similar to transition energy. To know about transition energy, watch the first video. I have solved a question regarding transition energy. So since cyclobutadiene is formed from 2 ethylene molecule, so since cyclobutadiene is formed from 2 ethylene molecule, and energy for the MO for ethylene molecule, for there will be two energy state. First energy is alpha plus beta, and the second MO energy will be alpha minus beta. You can apply the rule for acyclic system, and for acyclic system energy formula is E is equal to alpha plus 2 beta cos k pi by n plus 1. Here k will be 0, 1, 2, 3. Not 0, only k will be 1, 2, 3, etc. For cyclic system, k will be 0, plus minus 1, plus minus 2. And here n is equal to number of carbon atoms. So for the first orbital, the energy will be alpha plus 2 beta into cos k will be 1 and n here will be 2. So cos pi by 3, that means cos 60 degree, and the value of cos 60 degree is equal to half. So first energy will be alpha plus beta, and for second orbital the energy will be alpha plus 2 beta cos k will be 2, so 2 pi by 3. It is 120 degree, and value of 120 degree is equal to minus half. So second orbital energy will be alpha minus beta. And since cyclobutadiene is formed by combination of two ethylene molecule, and in case of ethylene molecule the electron is distributed like this, so for one ethylene molecule energy will be 2 into alpha plus beta, so the total energy will be like this, that is 4 alpha plus 4 beta. And the delocalization energy we can get by subtracting this energy, that is 2 ethylene molecule energy, from the cyclobutadiene energy. That is energy of cyclobutadiene is equal to 4 alpha plus 4 beta, and energy of 2 ethylene molecule is 4 alpha plus 4 beta. I am again telling that this is not similar to transition energy. Transition energy is different thing. So delocalization energy for cyclobutadiene is 0. Is it okay? Similarly, you can also calculate delocalization energy for the benzene case. Just calculate the 3 different energy level using this. There will be 6 molecular orbitals, so 6 energy level, and you have to apply this formula since it is a cyclic molecule, and you will get E1 to E6 energy. And since there is 6 electron, the electron will be distributed between 3 molecular orbital, and if you calculate the energy, you will get a 6 energy orbital will be E1 will be alpha plus 2 beta, E2 and E3 will be degenerate and their energy will be alpha plus beta, and E4 and E5 will be degenerate, their energy will be alpha minus beta, and E6 energy will be alpha minus 2 beta. You can calculate this energy by putting the value of K from 0, plus minus 1, plus minus 2 and plus 3, and N in all the case 6. You will get this energy calculation. And since benzene molecule is formed from 3 ethylene molecule, so for 3 ethylene molecule you have to calculate the energy following this rule. There will be 6 alpha plus 6 beta for 3 ethylene molecule, and if you calculate the energy of the benzene system, that means total energy for benzene will be, there will be 6 electron distributed in 3 molecular orbital, that is 2 electron in E1 and 2 electron in E2 and similarly 2 electron in E3. So total energy will be 2 into alpha plus 2 beta, and since these two are degenerate, so there will be 4 alpha plus beta. Since in E2 there will be 2 electron, E3 there will be 2 electron, that means 4 electron. So 4 into alpha plus beta. The total energy will be 6 alpha plus 8 beta, and for 3 ethylene molecule you get energy is equal to 6 alpha plus 6 beta. Then delocalization energy will be, you have to subtract this value from the energy of benzene molecule, so delocalization energy will be 2 beta. Is it okay? Try it by yourself. If you feel any difficulty, then let me know in the comment section. Here in this case I want to say one thing, that in all the cases for cyclobutadiene or benzene, I am telling one thing repeatedly, that cyclobutadiene is formed from 2 ethylene molecule or benzene is formed from 3 ethylene molecule. The term is not right. We can say that cyclobutadiene molecule contains 2 ethylene moiety, and similarly benzene molecule contains 3 ethylene moiety. So to calculate the delocalization energy, we have to subtract the energy for 2 ethylene molecule to the energy of the pi system of cyclobutadiene molecule, and similarly for calculation of delocalization energy of benzene, we have to subtract the energy corresponding to 3 ethylene molecule to the energy of the pi system of benzene molecule. Is it okay? Next, let's solve how to calculate the normalized hybridized orbital from a given wave function. Now this is the given question. We have to identify the correct normalized wave function for the sp2 hybrid orbital from the 4. Now if a wave function is given like this, C1 Ψ1 plus linear combination of different atomic orbital, then psi will be normalized. If the summation of the square of this factor of this atomic orbital is equal to 1. That means if C1 square plus C2 square plus C3 square is equal to 1, then psi will be normalized. There is another thing you have to learn, that the contribution of psi1 atomic orbital to this wave function is equal to C1 square, and similarly the contribution of psi2 atomic orbital to the given wave function is C2 square, and similarly the contribution of psi3, the contribution of psi3 to the psi is equal to C3 square, and the summation of this square will be 1. Now to find a normalized wave function, you have to satisfy first this condition, and next if you are given that you have to identify the sp2 hybrid orbital, that means contribution of s in the total wave function will be 33%. It is from the rule of sp2 hybridized orbital, and contribution of p atomic orbital to the given wave function will be 67%. That means the ratio of s and p atomic orbital will be 1:2. It is the contribution ratio. So you have to find that which given wave function is satisfying this condition. Now you can go through two different pathways. That first you check this condition, that the summation of the contribution of the each atomic orbital is equal to 1 or not, and then if two wave function satisfy this condition, then you have to check the second option, that is the contribution of each atomic orbital to the given wave function. Okay, or you can go in the reverse way, that first you check the contribution of S and P character, then you just check the normalization condition. Now I am proceeding as the first logic, that is calculating the summation of the contribution is equal to 1 or not. If you calculate for the first case, then the summation of the square, that is summation of the contribution, will be like this. That means 3 by 9 it's not equal to 1. For the second case, the contribution of different atomic orbital will be like this, and if you sum up these 3, then it will be 2, it will be 4, it will be 1. That is 7 by 6 is not equal to 1. In the third case, the summation is 1 by 3 plus this square, that means 1 by 2, and C3 square, that is 1 by 6. If you add these 3, then it will be 3, 2 plus 3 plus 1, that means 6 by 6. It is equal to 1. Let's check the last condition, that is summation of the square. For the last one is 1 by 3, and it is 1 by 12 plus 1 by 6. 4 plus 1 plus 2, that is not equal to 1. So the first condition is satisfied for this case. Now let's check the second condition, the contribution of the S and P character. Now for the third case, the contribution for side 2S is equal to 1 by root 3 square, 1 by 3, and the summation of the contribution of P character, S character, it is P character. P character will be 1 by 2 root 2 square divided by 1 by root 6 square, that is 1 by 2 plus 1 by 6. If you add these two, it will be this, that is 4 by 6, that means 2 by 3. And since the contribution of 2s atomic orbital is 1 by 3 and P contribution for P character is 2 of 2s, that means it is satisfying the condition for sp2 hybrid orbital. Since for sp2 the S and P character ratio will be 1:2, and here S and P character ratio is equal to 1 by 1:2, since the P character is double the S character. So the sp2 hybrid orbital, normalized sp2 hybrid orbital is this. Now let's go to the second question. Similarly, here you also have to find a normalized sp2 hybrid orbital from the given 4. So as I previously performed, here I am going through the same logic, that first I calculating the summation of the contribution, that is for A, that is 1 by 9 plus 1 by 9, 1 by 9, it will be 3 by 9 not equal to 1. In this case 1 by 4 plus 3 by 8 plus 3 by 8, that the summation will be 2 plus 3 plus 3, and it will be 8 by 8, so it is 1. So for the side 2, the summation and the contribution summation is 1, and in the third case it is 1 by 3 plus 2 by 3. In this case also contribution summation is equal to 1. In the last case, the summation contribution is equal to 3 by 9, so not equal to 1. That means we find that for B and C hybridized orbital, the first condition is satisfied. Now we have to go for the second condition, that is the contribution of S and P character. For second wave function, contribution for s orbital will be c1 square, that is 1 by 4, and for p character contribution will be it is 3 by 8 plus 3 by 8, and it is 6 by 8, that means 3 by 4. Is it okay? That means the ratio for S and P character, you can see that it is 3 of S character. 2s means 2s atomic orbital. So the ratio of S and P character is equal to 1:3, but for sp2 hybridized orbital it should be 1:2. So it is not the sp2 orbital. Now let's see for the third case. The contribution for the 2s atomic orbital will be 1 by root 3 square, that is 1 by 3, and for the p character will be root 2 by 3 square, that is 2 by 3. It is equal to 2 into 2s character, and for this atomic hybridized orbital, ratio of S and P character is equal to 1 by 2, that means sp2 hybridized orbital. So we can say that this is the exact normalized hybrid orbital. Here it is some mistake, that is it is contribution for this atomic orbital, and the contribution will be 4. Since we are taking the summation, so it will be 5 and it not equal to 1. So that's all for this discussion. If you like it, then please share it and please subscribe to my channel. Thank you.